So we're on May the 3rd. May the 3rd, 2016, and this piece is about an analogy of the universe, of how to map the universe. I have no idea if this is probably one of those ideas that I think is original, but probably isn't, because, you know, there's people an awful lot smarter than me who have thought of all this stuff before. But just as an idea, I'll kind of throw it out there. And this is to make me look more intelligent. Okay, cool. Doesn't work. Doesn't make me more intelligent, let's put it that way. So, the universe is basically, space is full of space. And it is not only full of space, but there's very few features in it, really. There is there's the vast vacuum that is basically seems to be most of the space. Big black vacuum of nothing with no air and cold, dark and unpleasant. And basically you've got that empty space that seems to be a vacuum punctuated by planets. I mean, basically lumps of rock and gases at different temperatures. Then the only other thing you seem to have, and again I don't know a whole lot about it, but the only other thing you seem to have basically is something like a black hole or a wormhole. And these things are, these seem to be the only features. You've got a load of space at a vacuum, low pressure, and then you've got the stars, which are the suns, which are a big ball of material that seems to be continually in a nuclear explosive state, and there's some core obviously that feeds all that. And then you've got the black holes or wormholes, I'll explain that in a bit. And I'm not sure how many more features there are. Yes, there's lumps of rock, and you call them planets if they're a certain kind, and you call them asteroids if they're only little things, and all the rest of it. Basically it's either solid or a gas or a mix of those things. And like Mars, you seem to have liquid water, they think, that's been turned into ice, so it's frozen stuff. There aren't that many different kinds of features. The thing I wanted to say was that the concept I'm going to try and get across is that, to me, what we should do is model space, the universe, using weather system computers. I don't know if you know, but it's famous that the weather system computing power required is massive, because you have to put in so many parameters into it in order for it to work anything out. So modelling the weather turns out to be quite complex. But the things you have to model, you've got the sphere that is the Earth, and then you've got this balloon round it of gases, and they behave in a pretty complicated way. And you've got basically high pressure and low pressure, and then there's moisture and stuff, and basically how someone explained it to me was, my brother said it was like, it's the low pressures that cause everything. You could think of it that way, you can think of it different ways, but one way to think of it is the low pressures cause everything, because they are like vacuum. It's like a hoover, it sucks the bad weather in, so things get sucked into low pressure. Low pressure equals a vacuum, so the rain gets sucked in because this is low pressure here, let's say, and it's high pressure over there, so this sucks all the dirty stuff in. Sand, dust, debris, radioactive particles, soot particles from diesel, rain, ice lumps, you know, everything that can be sucked in gets sucked into this vacuum, so the low pressure areas suck all the mucky weather in. Hence you're looking for high pressure when you want the weather to improve. So, you know, we've got these pressures, and you have a barometer, and as it goes up, that's why you tap it to see if it's going up or down. It's not so much the setting the barometer sits at as whether it's getting there by coming down and up to there, or whether it's coming down from somewhere else. So it's what you want is that barometer's moving up, the pressure's increasing. That means all the dirty weather's getting sucked out to somewhere else. And there are multiple somewhere else's, because you go to different places in the world and there's different low pressure zones. And they're always moving. Right, so my point is, outer space is mostly a low pressure zone. It seems that way, and yet, although we call it a vacuum, the black holes or wormholes are actually even more of a vacuum. So the analogy I was going to draw was that tornadoes effectively are super low pressure areas which whirl into a cone and act as a massive, powerful vacuum of low pressure that can suck houses and trucks and cars up. And deposit them. Once they're sucked up, you see, they spin round in the cone. It's very narrow at the bottom where it is the ground, which is why it's so concentrated and rotates so quickly and causes so much damage. And then it loses energy as it goes up to the top of the cone. And eventually it picks a truck or a car up or something, and the force that it's got whirling it round, and it becomes less as it gets to the top of the wide bit of the cone. So then it's got to drop the thing. And depending on what the last force was acting on the car or house as it's getting rotated round, it gets let go. And when it gets let go, it's going to then drop, just as if you'd slingshot it. It just has to go and drop following the force that it was given. Because no longer is it in the really active part of the cone which is able to hold it up of the tornado. And I'm just saying that black holes are very like that. Or wormholes, whatever you want to call them. Einstein came up with an equation, and he's famous for this equation, E equals mc squared. I think I've got it right. And he came up with this equation, called the most famous equation in the world, famously. And that his equation has solutions, mathematical solutions, that, I don't know if it's that one or another one, but his equations have mathematical solutions that mean that something called a black hole, which is basically a funnel, that is big at the side that we would see and goes down to a tiny, 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 tiny point down the end of a funnel, a cone type funnel. And they call that end point the singularity because it comes down to a tiny, tiny little thing. So all these things get sucked into that black hole and it squashes them and crushes them with gravitational pull. And that's from a massive star having compressed and collapsed. Because the bigger something gets, the more mass it has, the more gravitational pull it has to the centre of itself. So eventually it becomes more pressure than even solid matter like rocks can take, and they will crush and collapse into something even smaller. But those are the kind of forces we can't even imagine. But if something gets big enough and heavy enough, it will do that. So Jupiter, being 2.5 times the mass of Earth, makes you 2.5 times as heavy. You take the same mass but put it on Jupiter, you're 2.5 times as heavy. Now, there's nowhere to stand on Jupiter because it's a big ball of gas. But even though it's a big ball of gas, it's incredibly heavy. So you can imagine a lot of things get attracted, because big things in space attract little things. So the bigger something is, the more it's like magnets, like having a bigger magnet, it pulls things in. So I guess for a while, Jupiter is going to pull in little asteroids and little chunks of rock that come by. And eventually, as it gets heavier and heavier with gathering these chunks, it's eventually going to get so heavy, it's going to be able to pull planets in from quite a distance. And then it gets so heavy, it just can't, the matter that it's made of can't even support itself. And then it collapses in, and then you get this thing called a black hole. Now, the interesting thing is that Einstein, who died in 1955, his equations we've relied on to get to space, to the moon and way beyond, even though there's meant to be some irregularity with them. But they're awfully good considering the guy, didn't have the benefit of having space travel and exploration behind him and stuff. So he had a mathematical theoretical solution which is satisfied. There's two solutions that satisfy his equation. One is a single cone shape, which it would be a cone like that if that camera were the singularity, the densest piece at the end of this cone. We'd be in space on Earth, we'd be looking out to space and we'll see this cone because it's very dark, because it's so heavy it even sucks light in. So it disappears into a tiny little speck. A wormhole, you'll know, is a way of disappearing to another part of the universe, supposedly. But we have to be careful about this. Einstein didn't believe in black holes, even though he had postulated that it satisfied his equation, such a thing to exist. A wormhole similarly exists, but it's like two black holes put together. So you've got two narrowing funnels, yeah? And they're joined together at a narrow point. And the idea is you get sucked in one side and you get blown out the other. And there's a great way of showing this, which is to see if you wanted to travel. There was a movie called Event Horizon where they showed you this. It's hard if you want to travel from one point to another in space, because that there is 10 billion light years or something. But a wormhole makes you be able to do this thing. So you have a wormhole there and a wormhole there, and you can fold space, treat it as if it's folded, and then you're right there. They're in the same place. So what a wormhole is meant to be really is some bit of space billions of miles away, and where it meets in a tiny point, that's this bit of space right beside us. And then your distance is nothing. Yeah? Of course, you've got to travel through a wormhole to do it, which we already seem to think is crushingly painful. So how would we do it? I have no idea. How could you withstand that? What would withstand it? I don't know. But that means it's mathematically possible. But the reason why Einstein was skeptical and why he's such a smart bloke, or was such a smart bloke, is because he knew theoretically it was possible to have a black hole. But in reality, it might not be. So here's how that works. 1 times 1 equals 1. So here's one apple, and I've got one of it. So that's 1 times 1 equals 1, okay? One apple, and I've only got one of it, that's 1 times 1 equals 1. But the mathematical equation of something equaling 1 is also satisfied by negative 1. Negative 1 times negative 1 also equals 1. But you can't have a negative apple, because a negative apple just wouldn't be there, would it? I don't know, is it an inside out apple? But my point is, the theoretical answer is that both minus 1 times minus 1 equal 1 and 1 times 1 equals 1, but only one of them has a physical manifestation that we can interpret. So Einstein was wary of his equations having a result that meant that some weird thing like a black hole existed, when he didn't really know if physically there was a manifestation of that. Yeah? So it's that I've tried to explain as best I can. So in other words, I'll tell you what there is though. Einstein was very, very smart. Never been proven wrong yet. Okay? We've had a lot of science, a lot of computer power after he passed away, and we've never proven, we've relied absolutely on the guy's equations. So here's what I say. Einstein thinks that both a black hole and a wormhole, which remember is a double funnel, both of those satisfy his equations. So what I can say definitely is one of those definitely exists. I just don't know which one. Either black holes exist, or a double funnel exists, which is a wormhole. But in any event, one of them definitely exists, because he wasn't daft. And I'm saying that a bit like that negative 1 times negative 1 problem, one of them will have a real manifestation. It's possible both exist, but here's the problem. The reality is that if you physically got near a black hole, by the time you go into it to check out whether it's got a way out into somewhere else in the universe, and it's actually a wormhole with two ends, you're crushed to nothing at the bottom in that singularity, that speck of incredibly dense matter, before you find out whether you get squirted through or not. So anyway, my point is that if we treat the universe and the black holes as, if we use the weather system computing model to feed that information in, we should be able to get a bit further with how we think about the universe and black holes or wormholes. Doesn't matter. To us, they're the same, because we can only see the funnel that points towards us. We can't see beyond such a point because the light gets sucked in, so it all goes dark. There's a certain section where it all goes dark after that. We can't see anything. Maybe radio waves can go in and come back out. Maybe you could bounce something in and out, but light all disappears. I don't know. Everything seems to disappear. That point of no return, as it were, for light is called the event horizon. Hence the movie name Event Horizon that I was talking about, where he showed that experiment, how to go fast from one place to another using a wormhole. I'm just looking through to see if there's anything else here I wanted to talk about. That's basically it. And we treat the black holes or wormholes, as I say, they'll look the same to us from our side of the universe as well. We treat them as though they are tornadoes. And in fact, they are. I was thinking they're really dense, but of course, a tornado is in effect densely packing stuff together. It sucks everything together. It takes a house from over there, a human being from here, a cow from there, a car, and squashes the lot together. Yeah? So inside a tornado, it gets pretty dense. If there was enough stuff sucked up, it'd be rock solid. Right, so in fact, the black holes are equivalent and analogous to our tornadoes, and the bulk of space is equivalent or analogous to the air that isn't at massive pressures, or is it relatively benign high pressures. And you could feed that into the weather system and start to say, well, could we start to predict things once our computer model gets a handle on all that, and that our weather system is analogous, and it's also infinite because it goes all around the Earth and it never ends. I thought of it as being like a load of squeeze boxes put together. There's some that squash, and there's some that pull apart, right? And they're all attached to each other, so they're going, right, all around the Earth, but they never end. They're all attached in a loop, and it's just never ending, and they reconfigure all the time. And so space is like that. And you say, well, they think we've got one massive, big, super... This is just conjecture the scientists have, but they think of one massive super vortex, super black hole right at the centre of the universe where the Big Bang was. But you might say, why aren't we sucked in there? Well, for a start, there's inertia. We're all thrown out by the Big Bang. So it'd take billions of years for that changing into a black hole to affect us all, yeah? To slow us all down enough. But also there's all sorts of other black holes all around the place. So if where our little galaxy was here, there's all those little black holes everywhere, and big ones and little ones all over the place, which probably kind of even out. So it's a weird kind of equilibrium goes on. So there's some pulling us over that way, some pulling us... So in the end, we're kind of clumped together around the nearest thing to us that's big and heavy, which is the sun. If you wanted to model it, you could take it as just the sun, because where the sun goes, we follow. So if the mass of our sun get drawn into something, like a black hole, we just follow it in. And there's no way to stop that. So that's my idea, that you could model the universe, basically black holes and all the space and the lumps of stuff, which in weather terms is like chunks of ice or something. You could map that and predict with it if we could model it in the weather computing power that we got. I mean, nowadays you can take the internet, of course, and you've heard of that distributed computing thing where you borrow people's computers. Sometimes it's done illegally, of course, but you borrow people's computers to do the computing power. So although you've only got little computers, PCs or Apple Macs or whatever, if you can borrow everyone's to process, then you've got millions of computers, which add up to a lot of computing power. And people have done it on a voluntary basis. You know, the BBC have said, oh, there's this scientific thing going, this experiment going on, if you'd like to help, send an email to such and such. So that is basically it. And like I say, you'd be a brave man to bet against Einstein. So at least one of those things I say definitely exists. Einstein's too smart to be wrong. One of those things definitely exists. We just don't know which one. And both could exist, but if it's that negative 1 times an apple thing I was talking about, then it might just be a theoretical solution and not a physical solution. The physical version of that might not exist. But I say that definitely one of them exists. There's definitely one of either a black hole or a wormhole exists. And we just don't know which one. It could be both exist. I'm slightly doubtful about that. But he's such a smart guy and nobody's ever tapped his equations on the head. So one of them definitely exists, and it's just a question of which one. It'd be a lot more useful if it was the wormhole than the dead end, which comes to a tiny speck, but hey. So that's it, really. That's my way of having an analogy of the whole universe. Use our weather software. Thanks very much for watching and listening.